Hi all, this is Mr. Yeager for chemistry, and we are looking at the large topic of enthalpy today. So this is definitely a little bit longer in showing some concepts and then the math involved with it quite a bit. So what is enthalpy? Okay, so leading us first, going back to the prior prior part of this, when we talked about heat and heat transfer. We now basically understand how to measure heat, okay? Again, how much heat is being released, how much heat is being absorbed, based on an object's heat capacity or heat or specific heat, again, depending on what you want to say. But what we need to look at now, that's just if you're heating the object up and it's staying the same state of matter. So the thing is, there are all sorts of things that could then happen in that matter. What happens if you have a phase change? What if it's chemically reacting? What if you're dissolving? So there are all sorts of situations where we are more manipulating the bonds, not just how fast the particles are moving, but actually manipulating and breaking bonds that will release some of this, again, chemical potential energy in the form of heat. All right? So that's what we need to basically figure out is we're going to determine the energy heat released or absorbed during a reaction. And this will also help tell us whether this is a reaction that we will want to call favorable or not favorable. Again, I've already described that. Favorable means the reaction would like to happen essentially on its own. We used to usually call this spontaneous, but it doesn't necessarily mean that it just immediately occurs and it's just like, ooh, it's spontaneous. It's not that idea of it happens, you know, whatever. This is why it would like to happen. So that's why we call it something that is favorable, versus a chemical reaction where you might have to add heat into it to make it occur, all right? And that would be considered not favorable because you're increasing the energy. So, enthalpy, the symbol for it is H. A lot of times you'll see this as delta H. Usually we're looking at a change in energy. That's the enthalpy. So the enthalpy, or also known as molar enthalpy, is just a nicer word for heat, a more technical word for heat that is released. That's why I usually say, that's why it's called H, all right? I mean, that's really nothing to do with that necessarily, but we can at least have that relationship that it's a energy being released in the form of heat, all right? And again, as I said at the beginning, we're going to use this for multiple situations. So phase changes. When we do phase changes, that will involve an enthalpy, all right, which sometimes we call heat of, heat of something. It's either enthalpy or heat of. We kind of interchange those two words. That's why I said enthalpy is heat. So we usually have some fancy words with this. We'll call it heat of fusion, heat of solid, heat of vaporization, heat of condensation, all right? What each of these represents are basically different phase changes. Some of them are kind of obvious. This is clearly the delta H of condensation over here, changing from gas to liquid, all right? And we would include a short little subscript abbreviation of what type of phase change is occurring. Vaporization is the same idea as boiling. You usually will see that as HVAP. Heat of fusion is our other common one that you will usually be given. That's actually for melting. So that one's actually a little confusing for some people because we know the word fusion means coming together. When we use it in the terms of phase changes, it's the melting of the substance. The nice thing is freezing is the enthalpy of solid, which you usually will see as Sol. Okay? So I'll talk more about those a little bit below, but these are specific values, constant values for particular chemicals. So we will see in a moment, water has one heat of fusion. It has one heat of vaporization. But if I'm talking about carbon dioxide, if I'm talking about ethanol, if I'm talking about ammonia, they will have different enthalpies compared to water, all right? But once you know which substance it is, these are all listed in a giant book where you can find all of these and essentially look them up when you need to use them as a scientist or as a chemist, okay? But again, going back to that real quick, this will show us whether we need to put energy into the process or whether energy is released by that phase change. So similarly, when I dissolve a solute, we have something called the heat of solution. The heat of solution, all right? And so again, that's just telling you whether heat is or energy is released or absorbed when something dissolves. This is again where we've done, we've dissolved sodium hydroxide into water and it gets hotter. That's because when sodium hydroxide is dissolving and splitting into its ions, it releases heat, okay? And then the last one is the heat of reaction, which we're going to be using quite a bit as well, all right? So again, all of these, kind of going back, we actually completely write out heat of solid because the heat of solution we usually keep as SOL. Heat of reaction is usually RXN, okay? So all of them represent energies. We could technically combine them. You know, they all have the same unit essentially, but we're not going to be combining all these processes in one problem. But energy is energy regardless of type. All right, enthalpy itself is going to be measured in joules per mole. All right, I know I write no there because again, we still have to continue using the mole. It can sometimes be in kilojoules per mole. All right, so just pay attention to the unit that's involved there. But it has to be per mole. So you're going to see in a moment, we're going to multiply the enthalpy times the moles to figure out how much energy is released. Okay? But from a qualitative perspective, well, I guess it's not qualitative, it's still quantitative. But without doing a lot of math with it, the enthalpy will tell us whether you have an exothermic or endothermic reaction. So again, to review, exothermic means energy is being released. When you have an exothermic reaction, you will have a negative enthalpy. So a negative enthalpy means that the overall energy of the system, of the reaction, of the reactants going to products, is a negative change, meaning you are decreasing the energy in your chemicals. And where is that energy then going? Out into the environment in the form of heat. Endothermic is where energy is obviously absorbed and you will have a positive enthalpy. That then feels cooler. Again, this confuses people, and I know maybe I talked about it before, but when you pull energy in, it's not like the object is absorbing that and getting hotter. It's actually being pulled into the bonds themselves or into the chemicals to form bonds. So that means it has to pull energy from its surroundings, and you're going to feel cold because it's taking heat away from you. So that's why it feels colder. Okay? So exothermic, you get a negative enthalpy. Endothermic, you have a positive enthalpy. Okay? So, because chemicals always want to have the lowest energy possible, reactions are seen as favorable when you have a negative enthalpy. So again, we'll see out in here, I might be asking you and say, hey, based on these enthalpies, is the reaction exothermic or endothermic, and is that favorable or not favorable? So clearly exothermic goes with favorable, endothermic goes with not favorable. All right, because we want to lower the energy to be a favorable reaction. Again, a reaction that would like to occur and can occur on its own. Again, that's what we mean by favorable or spontaneous. It's something you can set it there and it'll eventually do it on its own. You might not feel a lot of heat. This is not like all this heat's released immediately. It's when a mole of the substance goes, and maybe that takes some time. Okay? So if I look at these two, if a reaction has an enthalpy of positive 20 joules per mole, that means that this must be an endothermic reaction, and this would be not favorable. It's one that I can do, but again, when I say it's not favorable, I need to now put some energy into it to make it occur. Okay? Which might not be that difficult, but you're adding energy into the system, into the chemicals themselves, and therefore that's something they won't necessarily do on their own completely. Okay? If dissolving a substance has a negative 30 joule per mole enthalpy, that would be an exothermic reaction. We would feel heat, and we would consider that to be a favorable reaction. So that's how we kind of identify those. So that's something that's going to permeate through the rest of these problems. And a lot of questions I'll be asking where it's, hey, is this endo, exo, is this favorable, not favorable, why? And it's all about the sign of the enthalpy right now. Okay? All right, getting to some formulas, okay? Basically, I will list the formulas when we start using them. Actually, I'm going to probably just show them to you now, okay? What are the formulas for enthalpy, okay? A lot of times, at least the ones we're going to do, for phase changes, okay? What we're going to do, the formula will be Q. Q, remember, is heat or energy. Is simply equal to the enthalpy delta H times N. N is moles. So pretty easy. It's a pretty easy formula. Just enthalpy times moles. That's it. Okay? But I'm going to show you some problems of how we're going to use that. And again, that could be any enthalpy. We'll primarily be doing the phase change enthalpy. And again, that enthalpy can be positive or negative. So the heat can be positive or negative, okay, depending on what the enthalpy is. Moles, we got to be in moles. You're going to see you're going to have to convert from grams to moles again. Okay? So, a couple things. During phase changes, energy is needed to break and reform intermolecular forces, intermolecular bonds between the molecules. I'll kind of go over this probably a little bit more later when we do some heating curves and cooling curves. We'll talk about the formations of the different states of matter again and what's happening. But energy is needed to break those apart. We are not breaking the chemical bonds. We're not changing water into hydrogen and oxygen. We are just separating each water molecule away from each other if they're a solid or if they're a liquid, or vice versa, reforming those intermolecular forces that want to help hold those chemicals together, those molecules together. So the enthalpy is going to be used during phase changes. We use specific heat, Q equals mc delta T, when the temperature changes. But during a phase change, the temperature does not change. And again, this will probably be reviewed in another video later. But again, that's because all of that energy is not to make the molecules move faster, which is what temperature measures, or slower. It's to break the intermolecular forces. So therefore, we need that other formula, the Q equals delta H times N. And you can see I have here the different enthalpies for water. Okay, I should have mentioned that. These are all water. Okay, so the enthalpy of fusion for melting the water, for changing it from solid to liquid, is a positive 6.01 kilojoules per mole. That's what it is always to change a mole of water from ice to liquid. To freeze it, it's negative 6.01 kilojoules per mole. So again, what do you notice here? What do you notice about these two values? They're equal and opposite. Why? Well, because the energy needed to break those, to separate, not break, I don't want to say the word break so much, but to separate those water molecules from solid to liquid should be the exact same amount of energy they need to release to go back into the solid form. So if you know, like the thing is on a test, I usually will only give you the enthalpy of fusion or solid. It'll probably be the enthalpy of fusion because that's usually the one given in books. Solid is not necessarily given in a textbook or online because if you know the fusion, you know the solid. You know the opposite phase change occurring. Okay? The enthalpy of vaporization, that's the one I would generally give you. So that's the one changing from liquid to gas. It is 40.7 kilojoules per mole. Condensation would be negative 40.7 kilojoules per mole. All right? So I'm going to point this out. Let's go through this real fast. For solid, liquid to gas. Okay? Let me rewrite that. If I have melting, freezing, boil, and condense. Delta H condense, delta H vap, delta H fusion, and delta H solid. As you saw, as I go from solid, liquid to gas, I have to be adding energy, which makes sense because we talked about it way back in the first unit, that gases have the most energy in them. When elements or compounds are in their gaseous gaseous form, they have the most energy. Solids have the least amount of energy. Okay? And so, to go from solid, liquid to gas, I need to add energy in. So all of the processes going from solid, liquid to gas are endothermic processes. Okay? Because I'm adding energy into it. When I go from gas to liquid, liquid to solid, these are exothermic processes, which I know makes people go crazy. I know people will get this confused all the time. They're going, that doesn't make any sense. As it goes from solid, liquid to gas, I feel the heat, it's getting hotter. All right? The thing is, you're feeling the heat around it that the object's absorbing into it. All right? Technically, what's happening is it's actually pulling energy from something around it, and it's basically cooling some of the air around it while you keep on putting more energy into it. All right? That is why, again, we sweat. The reason we basically sweat is our body wants to have a liquid on us, and as that liquid vaporizes into gas, it cools our body down. All right? It actually cools the body. That's the purpose of sweating. All right? Because energy is being essentially released. It's being pulled from us, and that's where like that positive enthalpy, to change it, it's being pulled from the heat on our skin, which then cools our body off. All right? Which is a weird idea. It's an endothermic process. Well, as you go from gas, liquid to solid, it's an exothermic process. Energy is being released the whole time. The object's getting cooler and cooler and cooler. Again, weird, but why I wanted to point that out right now. Okay? But it's all related to the enthalpies. The other thing to already point out, you can see the enthalpy of changing solid to liquid and liquid back to solid versus liquid to gas. What do you notice about the numbers for the liquid to gas ones compared to the solid to liquid ones? The liquid to gas takes a lot more energy. Takes a lot more energy, all right, than changing it from solid to liquid. Why is that? When you are changing from a liquid to a gas, you are completely breaking those intermolecular forces, all right? You are completely pulling those particles apart. All right, because a gas is individual water molecules. While when you go from melting to freezing, freezing to solid, the particles still are staying together. You're just loosening them. So I always say that. I say the process of solid to liquid, liquid to gas is a loosening, slightly tightening, while condensation and boiling is a complete break or reforming of those molecules together, of those intermolecular forces. All right? So, quite a bit there, quite a bit to kind of see, but I like to point that out as well, okay? So I already pointed that out, okay? The process of melting and freezing and then vaporization and condensation have equal but opposite enthalpy values, okay? This is where I always have some people that are like, if I say, what's the melting point? I say 0, and then I say, what's the freezing point? And they'll tell me like -5. No, the freezing point of water is also 0. 0 is where it's going back and forth between melting and freezing, okay? Same thing with vaporization and condensation at 100 degrees. But again, energy is needed to melt, okay? Energy needed to melt is the same energy needed to release. This shows obviously the conservation of energy in these processes, okay? If I'm looking at solutions, there is an enthalpy of solution, H sol, that basically involves when you dissolve the substance, okay? We already mentioned it. This is why you feel a solution, maybe as you add something, it heats up or cools off. That is showing whether you have a positive or negative enthalpy involved. Okay? If it heats up, you have a negative enthalpy. If it cools off, you have a positive enthalpy. Okay? Energy's pulled in. So, I know, that's a lot. It's a lot to deal with here. Okay? We're good though. So, let's actually do a couple problems with that before I jump to Hess's law. Okay? You know what? I think I'm just going to make up the problem. Let's just keep life easy. All right. So let's say, for instance, I'm going to keep my life really easy. 36 grams of water. Let's say 36 grams of water that's solid, and I want to basically melt it. I want to know how much energy is needed to melt. Okay, so what I would be giving you here is I would say, well, delta H of fusion is 6.01 kilojoules per mole, and the delta H of vaporization is 40.7 kilojoules per mole. Okay, 40.7, I think I have that right. I'm sure I do. Let's just double check. Oops. Yep. I want to make sure I'm not using the wrong numbers. 40.7. See, I'm all right, panicking. Okay, yep, 40.7. I'm good. All right. Now I give you both, not to confuse you, but to sit there and go, which one should I use? Well, I said I'm melting. Well, that would be the delta H of fusion. So my formula is Q equals delta H times N. So Q equals delta H is 6.01 times, I'll keep my units so we understand that we're in kilojoules. And I just need my moles. Well, 36 grams of water, the reason I use that number, 1 mole is 18 grams, that would be 2 moles. So 6.01 times 2 moles is 12.02 kilojoules, because moles will cancel out. It'll take 12.02 kilojoules of energy to melt the water, to loosen those intermolecular forces and change every single gram of that water into liquid. Okay, that solid water, that ice, into liquid. But that's it. Okay, nothing too special there. I mean, I could get tricky here and say the opposite, where I'm like, hey, I have, let's do this. Let's say I have 36 grams of steam, of gaseous water, and I want to know the energy needed to condense it. Well, it would be the same formula, Q equals delta H times N. It would still be 2 moles, but what I need to watch out for here is while I'm going to use the delta H vaporization, I need to use the negative version of that. Condensation is the opposite of vaporization, so this would be for negative 40.7 kilojoules per mole. Okay, negative 40.7. So hopefully if I can do my math right, this is negative 81.4 kilojoules. So if I want to condense 2 moles of water, it's going to take negative 81.4 kilojoules, which is a whole lot more energy than needed to melt it. Okay? And this is energy that's going to be released. So I might say, was this exo or endothermic? This is exothermic. Okay? So that's what we look for there. Now, I could add a little bit more difficulty to this. Okay? I could do that, and I primarily only will do this with water because we know the numbers. But I could say something like, hey, I have 30 grams of, well, let's do another number. Let's just say 18 grams of water. All right, at, let's say, 70 degrees Celsius. Okay? I want to freeze it. I want to basically find the energy to freeze all the water. And I'll be nice at 0 degrees Celsius, but that should be obvious. Okay? So what I'd give you here is I'd give you the specific heat for liquid water is 4.184 joules grams times degrees Celsius. Okay? All right. It turns out that ice and steam have different specific heats. 4.184 is the specific heat for liquid water, okay? Which that's what this is. And then I'll give you delta H, and I'm not going to give you both of them, but I would give you the delta H of fusion is 6.01 kilojoules per mole. So what's going to happen here? Well, I need to first lower the temperature from 70 degrees down to 0 degrees Celsius. When I'm doing a temperature change, I would be doing Q equals MC delta T for this one. So this is where you're going to see us combine both the specific heat capacity formula, and the enthalpy formula. So this would be Q equals MC delta T. So this would be 18 times 4.184 times negative 70 degrees. That's the change in temperature. Okay? So if I do that, that is negative 5,271.84 joules. I'm keeping all my sig figs for the moment. Okay? All my sig figs for the moment. All right? But that's only to get it down to 0. But it's still liquid. I now need to change it from 0 degrees liquid to 0 degrees Celsius solid. So that's where I would do, not delta H, sorry, Q equals delta H of the solid times N. So Q would equal, I have to do the negative 6.01 times 18 grams. I did change it to 18 grams. I hope you guys can see this. I'm going to do it real fast. 18 grams of water is 1 mole. I purposely made it where it's 1. So this would be 1 mole. And so it's negative 6.01 kilojoules that's being released. Now the thing we got to be careful here is now I basically want to add these two together. This is Q and this is Q. They're both equal to energy. But this is in joules, so I need to change one to the other. I'm going to change the larger one. I'm going to change this to negative 5.27184. All right, I divide by 1,000 and then basically add the two together. So negative 5.27184 plus negative 6.01. That's going to equal a total energy released of negative 11 points. And I'm just going to round it off to 1 digit. I know that that's not necessarily the sig figs, I'm sorry. But I'm just going to leave it like that, kilojoules. Negative 11.3 kilojoules. I guess if we want to be really correct, I'm ignoring the temperature. I'm going to keep 2 sig figs, so negative 11 kilojoules would be my final answer. Okay? So that's where we get with all of it. That would be our energy released. So that's how we initially use a lot of this enthalpy formulas. I'm going to stop there. I'm going to do Hess's law separately just because I don't want this to go too long. So that is everything at this point, introducing this delta H value and showing you how we can connect it with the specific heat formula as well. All right, thanks.